Hey everyone, welcome back. Today we are going to talk about different types of solar panel installations. We'll focus on three main kinds: rooftop, carport, and ground mount systems. Each type has its own benefits and uses. So let's dive in. First up, rooftop installations. As you can see in the picture, this is on a roof. These solar panels are placed on the roofs of buildings, whether they are homes or businesses, or any commercial building. Rooftop solar is great because it uses a space that's already there, which is super important in crowded cities where land is limited. One of the best things about rooftop solar is that it can lower energy costs for homeowners and businesses. By using the sun's energy right on site, you can save money on electricity. Plus, many places offer incentives and rebates to make rooftop solar even more appealing. The second one is the carport system. Let me go to the carport. Yeah. So let's talk about carports, also known as canopy systems. These are structures built over parking areas, providing shade and shelter for vehicles while generating solar energy. They are designed to protect cars from the sun, rain, and snow. Carports can fit different type of vehicles from regular cars to bigger trucks. The solar panels on these structures can produce a lot of electricity, which can be used for nearby buildings or to charge electric vehicles. On the top of that, carports can make parking lots look more modern and eco-friendly. And then we have the last one, the ground mount systems. Now let's discuss the ground mount systems. These are installed directly on the ground without any overhead structures. You'll often see them in open spaces like farms or large commercial areas. Ground mount systems are flexible in design, allowing them to capture sunlight effectively throughout the day. They work well in places with plenty of land but not enough rooftop spaces. Some ground mounts even have tracking systems that move the panels to follow the sun, which helps produce more energy. Now, we'll see the difference in brief, the difference between ground mount and the canopy installations. So, what is the difference between carports and ground mounts? Ground mounts are installed directly on the ground without cars underneath, while carports are specifically designed to cover parked cars. Also, carports are usually taller than ground mounts, which can help their stability and wind resistance. We'll go into detail, much detail for all three types of installation, but let's go back to rooftop and let's start with their um, detailed introduction. Ooh, okay. Now let's dive into rooftop systems, focusing on a type called the ballast system. This is a popular way to install solar panels on flat roofs, which are common in many commercial buildings. So what is a ballast system? It is a method where solar panels are held in place using heavy blocks. These are the heavy blocks I'm talking about, kind of like big bricks. These blocks are placed on the panels to keep them secure, especially in windy conditions. The idea is that the weight of the ballast helps prevent the panel from lifting off the roof. Ballast systems are specifically designed for flat roofs, making them easy to maintain and stable. Sometimes anchors also used along with the ballast to provide extra security, especially in places with strong winds. So instead of the ballast blocks, we will have the anchors here. To distribute the weight evenly, we use components called chassis, and this is the chassis. Chassis. That's the spelling. But I mean, when you know the spelling and you will read it, I call it chassis, but the correct pronunciation is chassis. So yeah, these are these chassis are like channels where the ballast is placed, as you can see in the diagram. By spreading the weight out, we can keep the panels steady and functioning well, which helps them produce the most energy. The effectiveness of a ballast system depends on a few things: how heavy the ballast is, the roof design, the local weather conditions. Generally, the more weight means better stability. So it's important to consider these factors during installation. In areas prone to extreme weather, like strong storms or tornadoes, structural engineers often recommend adding more ballast blocks for extra security, because it will add up more weight and that will keep our modules on the roof, you know. They might also suggest adding more chassis to help hold everything in place, like chassis in between, um, at this place, in between the module. Like these two are at the end of the modules, but they can suggest and they can recommend to place the chassis in between as well. In a typical setup, chassis are usually at the end of the panels, and sometimes they are shared between two panels to help balance the weight. In windy areas, extra chassis may be added in the middle of the panels for added support. Structural engineers, I'm talking about, structural engineers take all of this into account while designing the system. They analyze local conditions like wind speed and the roof structure to make sure everything is secure and can handle bad weather. So let's talk about a key feature of ballast system. They don't require any roof penetration unless you are using anchors. This is a big difference compared to the other mounting systems like flush mount, which need to drill holes to secure the solar panels. And we'll come to flush mount system next. The ballast system relies only on weight to keep the panels in place, so the roof remains completely intact. No holes means no risk of leak or damage to the roof over time, which is a huge plus, especially for flat roofs that often have waterproof membranes. But with every benefit, there are some downsides. One downside of the ballast systems is that the added weight. Since we are not making any penetration, we depend entirely on those heavy ballast blocks to secure the panels, which adds extra weight on the roof. For example, a standard solar panel weigh about 40 kilograms. If you're installing hundreds of these panels on a large commercial roof, the weight can really add up. Each ballast block adds another 4 to 5 kg or 3 to 4 kgs. And if you use several blocks for each panel, the total weight can become significant. This could be a problem if the roof isn't built to handle that extra load. That's why it's super important to have a structural engineer evaluate the roof's load bearing capacity before installation. Overloading the roof could lead to serious issues, even collapse, which we obviously want to avoid. Now that we are covered ballast systems, let's move on to another type of rooftop installation called the flush mount systems. Flush mount systems are very common in residential solar setup, making it about 95% of the residential rooftops. Yeah, about 95. Most of these roofs are sloped, and the flush mount system takes advantage of that. The solar panels are installed parallel to the roof slope. So if your roof is sloped at 20 degree, and the panels will also be at a 20-degree angle, this is different from ballast systems where panels are installed on flat roofs. One of the great things about flush mount systems is that their simplicity. The angle of the panels is already defined by the roof angle. As you can see in the diagram, the angle of this roof is the angle of the solar panel or their slope. So there is no need for extra material to create a tilt. This makes the installation easier and can lower costs. However, flush mount systems do require drilling into the roof. These penetrations are necessary to securely anchor the system. Luckily, modern mounting hardware and flashing techniques have improved a lot, which helps minimize the risk of leaks from these holes. Now, the third one, which is rare, but yeah, fixed tilt system. This is the third type of rooftop systems, the fixed tilt systems, it is called, not to be confused with the fixed tilt ground mount system, on which will come Next, this one is kind of a mix between ballast and flush mount systems. Fixed tilt systems are usually used on flat roofs, just like the ballast system, but instead of using heavy ballast blocks, they rely on anchors, um, similar to what you can find in flush mount systems. So that's why I'm saying this is a mix of a flush mount system and a ballast system. So, yeah, some anchors, which is not clearly seen in this picture, but yeah, if you go to Google and you will see a fixed tilt rooftop system, you will see anchors there. In a fixed tilt system, the solar panels are set at a fixed angle, which is, of course, the name suggests, which is determined by the racking system. This angle is optimized to capture as much sunlight as possible, typically between 5 to 10 degrees. Unlike flush mount systems that follow the roof slope, fixed tilt systems give more flexibility in how the panels are oriented, making them perfect for flat roofs. Okay, next up, let's discuss the carport systems or the canopy PV installation. Carports are solar. I'm habitual of saying carports, so I will be using carports, but there is another name called canopy. They have another name called as canopy. So um, yeah, but I will still be using carports because I'm habitual of it. So carports are solar structure built over parking lots. They serve two main purposes, generating solar energy and providing shade for parked vehicles. As you can see, these systems are mounted over parking areas with solar panels installed on the top of the canopy. Usually the canopy is about 13 to 16 feet high. I guess 10 to 16 feet high, I should say. Yeah, 10 to 16 feet high, which is enough to fit cars and small trucks beneath them. Carport systems are a fantastic way to make the most out of parking spaces. They not only generate clean energy but also protect vehicles from harsh weathers. Plus, some carports can even have electric vehicle charging stations, adding even more value, which we have seen recently. Now let's come to the ground mount systems. So when it comes to ground mount system, we first need to distinguish between the fixed tilt systems and the tracking systems. The height of these installations typically ranges from 3 to 5 feet, depending on the specific design and local conditions. Now, let's dive into the ground mount fixed tilt system installation first. This system has two main types, the fixed tilt system and the tracker system. To keep things clear, we'll focus on ground mount fixed tilt so there is no confusion with the rooftop systems. The ground mount fixed tilt, as you can see in the diagram here on the screen, it sits directly on the ground, which is a big difference from the rooftop setup. Since there is no roof, we can't use roof anchors. Instead, the system relies on piles. These are the piles structures. These are the pile structures driven into the ground to secure the solar panels. These piles are usually installed about 4 to 5 feet deep into the ground to ensure stability and prevent any movement. The piles are placed at regular distances across the array to provide uniform strength and support. This structure helps the entire system withstand environmental stresses like wind and heavy rain, keeping it sturdy over time. Next up, ground mount single axis tracker PV installation. This system is designed to boost energy production by following the sun's path across the sky. Tracker system is divided into two types, single axis and dual axis tracker. So let me first go to diagram. As you can see in the diagram, a tracker system uses a motor. They have a motor here, which I think I should show. Yeah. Okay, motor. This is the motor, right? This is the motor I'm talking about. So this motor is used to adjust the solar panels throughout the day, ensuring they are always at the best angle to capture sunlight, as you can see in the diagram here. For example, A single axis tracker system can rotate along only one axis, allowing the panels to tilt towards the sun as it moves from east to west. Here's how it works. When the sun is in the east, the solar panels face that direction, as we can see. As sun as the sun travels across the sky, the tracker adjusts the panel's position to keep them aligned with the sun's rays. The motor detects how bright the sunlight is and moves the panel accordingly. So in the morning, they face east, and as the day goes on, they follow the sun and maximizing they follow the sun, maximizing the energy capture. And at the end of the day, um, when the sun sets in the west, they face the west. And next day, the same process starts from the east. The main advantage of tracking systems is that they can significantly increase energy production. Studies show that a single axis tracker can boost energy output by um, 20 degree to 30 degree compared to fixed systems, depending on where you are and the weather. However, tracking systems do come with some challenges. They are more complex to install and maintain since they have motors and moving parts that need careful attention. Plus, they have often the higher upfront cost compared to the fixed system because they have more parts to maintain, more parts to move, more energy they will consume because the motors have these tracker motors will also need some supply. So that is an increased load. Okay. Now let's compare the single axis tracker to um, the fixed wheel system, which have their panels means the PV modules permanently set to face the south. This is important because in our hemisphere, yep, okay, sorry, this one, they are fixed. Okay, they are fixed to face in the southern direction, because um, because in our hemisphere the sun is mostly in the southern sky. If the panels face north-south, they wouldn't capture sunlight effectively. What I mean by that is if we have, okay, let's take a pen. The sun, oh, okay, the Earth is tilted at some angle, and the sun is here, right? This is the northern hemisphere, and this is the southern hemisphere. So when the sun rays come over it, and we are in the northern hemisphere, the sun rays will fall on the south side of the northern hemisphere. And that's why they're always, I mean, it is recommended to keep the PV modules face to the south so that they can capture more sunlight. For the northern hemisphere, in the diagram, the Earth is tilted at some angles, some 23.8 degree something. And this is the northern hemisphere, this is the southern hemisphere. And if we see in this diagram, the sun rays will fall like this. They will not like this, but yeah, something like this. And they will fall mostly on this side of the northern hemisphere, which is the south side of the northern hemisphere. And this side will remain um, deficient of the sun's rays, as I would call it. So, if the panels face north-south, they wouldn't capture sunlight effectively, and I'm talking about the tracker systems now, why the tracker systems are kept at east and west facing, not in the north and south facing, because of course, um, if the panels are faced north-south, they wouldn't capture sunlight effectively because there will be no sunlight in the northern part, or there will be sunlight. Obviously, there will be some sunlight, but not that much. making any tracker, which will make any tracker components unnecessary. So we orient the panels east to west, allowing the tracker to do its job effectively. While single axis tracker mainly move horizontally, it is essential for them to adjust correctly to maximize sunlight exposure. Now, there is another kind of tracker, which is the dual axis tracker. As you can see in this diagram, they move in two axes, in both X and Y. So in a single axis tracker, the panels rotate only along a horizontal axis. This lets them follow the sun's path from east to west throughout the day. In contrast, a dual axis tracker offers even more flexibility. It allows the panel to adjust both horizontally and vertically, following the sun's path more accurately throughout the day and across different seasons. To visualize this, think of it like this. As the sun moves from east to west, the dual axis tracker adjusts the panels in two ways. As you can see in the diagram, the horizontal movement is along the x-axis, the east-west. I would call it the east, the west, while the vertical movement is along the y-axis, which is north-south, which I cannot draw in here, or let me draw it here. No problem. North and the south. This ability to move in both directions significantly boosts the energy harvested because the panels can maintain the best angle throughout the day. Now let's clarify two important terms in the solar installation. Oh, yeah, this is um, you know, another diagram to show a real diagram to show the ground mount dual axis tracker PV installation. As you can see, throughout the day, this is how it will move, how the panels will move. They have their own tracker. They have their own tracker motor. I meant. Okay. So as we see this picture, and because we are talking about this, let me clarify two important things or two important definitions that we have used: the tilt and the azimuth. Tilt refers to the angle at which a solar panel is installed relative to a flat surface. So, for example, if we see this, the tilt of this is the horizontal axis. The tilt of this module will be this angle. If a panel is tilted at a 5-degree angle, that helps optimizing sunlight capture. This is just for an example for most ballast rooftop installation. Different tint angles can impact how much energy is produced depending on the location and the season. For example, in rooftop systems, mostly for flat surface, the tilt angle is around 5 to 10 degrees mostly that we take. And for this ground mount type system, this ground mount fixed tilt system, it is about 20 degrees or 25 degrees. So there is a huge difference. And for the tracker system, it is much more. For the tracker systems like this single axis tracker system, and also for the dual axis tracker system, this is like 60 degrees. If I'm calling this plus 60 degrees, then I will call this minus 60 degrees. So this is plus 60 degrees and this is minus 60 degrees. This is the angle, or this is the angle. I'm sorry. Let me redraw this. Yep. So 60-degree plus minus 60 degrees. This is the angle for tracker systems, and also for the dual axis tracker as well. This will be the angle for carports. For carports, I think it will be it is around 15. No, for carport it is less actually. For carports it is around 7 degrees to 10 degrees. That's all. 5 to 10 degrees. It is in between 5 to 10 degrees, and mostly 7.5 degrees is what we generally use for carport systems. So, and now let's talk about the azimuth. Azimuth is the compass direction that the panel faces. If the panel is facing this side, okay, it is measured in degrees from to north. For instance, if a panel faces south directly, if the panel faces south directly and this is the north, and this is the north direction, um, its azimuth is 180 degrees. 180 degrees. If the panel is facing east, it has a 90-degree azimuth. And if the panel is facing west, it has an azimuth of 270 degrees. So it will cover total this. So this is the clockwise angle from north to the point or to the angle at which the module is pointed at which the module is pointed. In our examples, like I've already said, for ground mount systems, you can see the tilt might be around, go to the ground mount system, the tilt might be around um, 15 degrees or even 20 degrees or 25 degrees. Um, Now, regarding the module tilt on rooftop, the angle aligns similarly to the roof slope. I'm working on an isometric drawing to illustrate this. Let me go to this. This is an isometric drawing. Oh, no, 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 no. Yep, this one. I don't know. Yeah, this looks more, but this is again isometric, so around 5 degrees to 10 degrees, sometimes more. Now that I think that's all for azimuth and tilt. Now that we have covered tilt and azimuth, let's talk about the installation guidelines for solar modules. These are specific rules for rooftop systems mainly. Yep. So types of roof, first of all. So when we are talking about the rooftop systems, we will first cover the types of roof. And we will focus on the residential installations only. In this slide, you can see there are two types of roofs for residential system. There are two types of roof, or for any type of system, any type of residential, any type of rooftop system. There are two types of roofs: pitched roof and flat roof. What are gable roofs and what are hip roofs? Now, um, a gable roof has two ends that don't meet. For example, this. A gable roof has two ends that don't meet, right? Forming a triangle at the top. A hip roof, on the other hand, you can see here, on the other hand, has ends that converge, giving it a more symmetrical look without separating edges or overhangs. And now let's break it down to the components, the parts of a roof. What do we call what? So first of all, a ridge. This is a ridge. The highest point where two slopes meet. This is a ridge. Eave, the lower edge that overhangs the wall. So eave is this. Yeah, yeah. Okay. Then rake, the sloped edge of the roof. Rake is this sloped edge. And then a valley. This is a valley, the area where two roof planes meet, helping with drainage. Understanding these terms is essential for discussing installation practices. Proper installation guides and guidelines ensure safety and efficiency, leading to optimal performance of the solar system. Next, we will look at specific installation rules for both cable and hip roofs, focusing on module placement, setbacks, and maintenance pathways. These considerations are crucial for compliance with local building codes and safety standards. Okay, maybe this will give a better understanding of what I'm trying to So, these are the parts which are inside the roof, which makes the roof structure. So again, roof types, if we are going to rewind everything for a moment, roof types, we heard about two roof types. One is hip roof, and second is the gable roof, mainly for the sloped roofs, not the flat roofs. So the slopy roofs or the tilted roofs are of two types, hip roof and gable roof. Hip roof, where the edges are connected, creating a symmetrical structure, and gable roof, where the roof features two sloping sides that meet at the top, forming a triangular shape. So again, this is the hip roof, where the ends are meeting, and the gable roof, where they are making a triangular shape, which are meeting at the top. Flat roof is much simpler in design. A flat roof is a flat roof, as we have seen in the diagram earlier. Skylights, other things we have covered, I guess, the ridge board, ridge, rake, a chimney, a skylight, our window. The skylights are windows set into the roof that allow natural light to enter, enhancing aesthetics and energy efficiency. Personally, I would love to have skylights in my home for their visual appeal and efficiency, but I don't have a skylight. Now, I guess that's the end of the slides, and we can go to the guidelines now. Now, okay. So, all right. Ridge setbacks. These are some of the guidelines when you are going to install modules on a rooftop system, and the rooftop system has the most, I would say, these rooftop installations have the most um, rules to follow or guidelines to follow. The carport and ground systems are simpler. They do have their rules, but not like these. But it is what we have. So let's discuss the rules for installing solar panels. For ridge setbacks on a non-sprinkled system, where um, on a non-sprinkler system, so setback from ridge, it is crucial to maintain a setback of 36 inches from the ridge if the roof is not equipped with a sprinkler system, and the PV system occupies more than 30% of the total roof area. In our diagram, the blue area represents the PV installation, which exceeds this threshold. Of course, it is more than 33%. So this setback ensures safety and accessibility for emergency personnel like firefighters who needs access to the roof in case of emergency. And we are giving a roof access pathway, so the firefighter will climb on the roof through this space, which is also 3 feet. Now, ridge setbacks on a sprinkle system. If the roof has a sprinkler system, if the PV area occupies less than 66% of the total roof space, the setback can be reduced to 18 inches, as you can see in the diagram. On both the sides, I'm talking about both the sides. Earlier, it was for both the sides again. The 36 inches or 3 feet was for both sides. Now it has been reduced to 18 inches on both the sides, but a 3 foot access pathway remains essential. If modules are confined to one side, which we can see on the other diagram. If the modules are confined to one side, the setback can again be adjusted to 18 inches, but the 3 foot access pathway must still remain. Okay, and ridge setbacks, again not sprinkled. When the modules are not on the other side of the ridge, yes, then we can make these 18 inches or total um, 36 inches. So 18 inches on this side, 18 inches on that side, so making a total of 13 inches. And The roof access pathway still is 3 feet or 36 inches. Now, if we have the sprinkle system again, which is greater than 66%, uh, so I missed this, so less than 33%. So it was the ridge setback where it was non-sprinkle, but the PV module area was greater than 33% or 33% of the total roof area. This was required 36 inches setback from ridge. And here it was non-sprinkled again, but this time it is less than 33% of the total roof area. The PV is acquiring or covering less than 33% of the total roof area. So in that case, we will have to use 18 inches of setback from the ridge on both sides of the ridge. And then if we come to this part where ridge setbacks enter the sprinkled system and the PV is acquiring or covering more than 66% of the total roof area, then again, it goes back to 36 inches of setback from the ridge on both sides, and roof access will remain 3 feet here. Well, not supported. And then, yep, setbacks and pathways involving hips and valleys. If you have a roof where hips and valleys are present, then this is how it will go. So the roof access you can give 3 feet. And the roof access pathways will always be on that side, should always be on that side. I should use the term should. They should always on the side where you have the parking area or you have pathways to your home, a driveway, I would say. So 36 inches from ridge on both sides of the ridge above PV. And you can, if not like this, then you can give it like this as well. So these are two variations of the same case. Or if you have PV on all sides, then you can give it like this as well. So these are actually three variations of the same case. And now, if there is a roof, an overhang below, for example, you can see there is PV and there is PV, then you can have the access pathway here as well. Okay, let me rotate this. So, this is for commercial buildings, and if the commercial buildings which are for the buildings less than 250 feet long, the perimeter offset must be a minimum of 4 feet. As you can see in this diagram, they have taken perimeter offset of 4 feet from the building, and the mid-axis pathways are 4 feet. Okay, so these are the mid-axis pathways. There's another way to reduce this mid-axis pathway or to, um, you know, oh no, that is for commercial buildings. So, okay, it's for commercial buildings more than 250 feet. I'm sorry. So for the commercial building less than 250 feet wide on either axis, you will have to give 4 feet perimeter 4 feet perimeter offset, and then mid-axis pathway as well is also required. And then these spaces, these cutouts that you see here are for any cutout vents. If there is any vent present on the rooftop, then you will have to give some access to it. You'll have to give an offset from that as well, a setback, say. So for buildings longer than 250 feet, the perimeter offset increases to 6 feet. Okay, so the perimeter offset has increased to 6 feet and the mid-axis pathway expand to 8 feet. So in this diagram, 4 feet, it still shows 4 feet, but yeah, this is the one. Okay, we'll come to that later, that other diagram later. But yeah, this is the one. This is the simple one. So you can see the building width is more than 478, is more than 250 feet, and length is also more than 250 feet. So the building perimeter offset has increased to 6 feet, and the mid-axis pathways are 8 feet here. If there is any obstruction, like HVAC units, the HVAC, as you call it, high voltage AC units, the skylights, or any roof hatches, that would require a 4 foot offset to ensure access for maintenance and safety. If the pathways are blocked by solar modules, the rationale for required offset becomes questionable. Access must be maintained for maintenance and emergency responses. So in this diagram, you can see these must be the vents, or these must be something, and and a 4 feet access or something is given to them. A space is given to them, open space. You can reduce this 8 feet parameter, 8 feet fire access or mid access pathway to 4 feet by giving 20 feet vent openings. By giving vent openings after every 20 feet. So these are the vent openings that I was talking about in this example on the left hand side. So they have given 20 feet, they have given vent openings after every 20 feet on both y-axis as well as the x-axis. Okay, so far we have explored essential rules for rooftop module installations, which encompasses various types of PV installations like rooftop, ground mount, and canopy systems. Understanding these categories helps us appreciate the nuances of solar energy development. Now let's delve deeper into guidelines related to ground mount and canopy systems, as many concepts overlap. For example, in a ground mount system, and I will go back to this from the current slide. Let's go back to the ground mount system. Mm-hmm. Yep. Okay. Okay, for example, in a ground mount system with multiple arrays, each array may consist of several rows of modules stacked in different configuration, as you can see. So there are 4 rows here in this diagram, and a row with a single module height is called one high. Okay, what I mean by that is this row is not having one single module, it has 2 modules. So if a row has multiple modules stacked, it can be classified as 2 high, 3 high, or even 4 high, depending on the arrangement. This classification is crucial for managing spaces and sunlight exposure. So in this diagram, this is 2 high module, or two high row, fixed tilt row, 2 high fixed tilt row. Now, the distance between 2 rows, we'll be talking about row to row spacing and pitch. And the distance between 2 rows of a module is known as row to row spacing. So this spacing, let me take, if I see this from the top, it would have been much better, but yeah. So this is spacing I'm talking about. This is called the row to row spacing. This measurement is vital for maintenance access and ensuring that shading from one row doesn't affect another. Okay, because the sunlight might come like this. Sun may be here, not like this, but yeah, sun may be here and it will come at an angle. And this angle, and then it will fall on this row, this front row, and the shadows of the front row will also fall back on the next row, which is not good for production, because if the modules of this row will be in shadow every time, then what will they produce? They will produce nothing. So it is very, very efficient. It is very, very important to keep a minimum row to row distance, um, so that you don't see, or your modules in the rows behind the front row do not observe any kind of shadow on them. Some shadow is fine, and we cannot get away with shadows like that. But yeah, we should try to keep them away as much as possible. We should design the system in a way so that the shadows will not fall on the rows behind. Okay, so there is another thing called pitch. The space between the centers of adjacent rows is called pitch. So if I'm saying, and let me erase this, and then I will redraw everything. The pitch that I'm talking about is this. Okay, so the distance from here to here is pitch. Here to here is pitch. Here to here is pitch. So these three distances will be same if the modules are same. Okay, if the module length is same, if we are using the same module here, same dimension modules here, then these three lengths will be same, and this is the pitch of the ground mount system. And even in the canopy systems, this is the pitch. Even in the rooftop systems also, this is called pitch. So pitch and rotor row spacing, these two things are common for all the systems. And the factor, the shading factor, or the shadow factor that I told you about is also applicable to both carport and rooftop systems as well. Now, let's discuss the ground coverage ratio. And this topic also is applicable to all three kinds of installations. Okay, so I'm talking about the ground coverage ratio, or GCR. This key metric in solar installation is calculated using the formula where GCR is equals to, um, well, let me first tell you what it is. So if you have the module width and pitch, you can easily derive the GCR. So the GCR would be modules width divided by the pitch. So here in this case, when you have two high modules, so module width will be this much. Okay, module width will be this much. This is W, let's call it W, and this is the pitch. So W by P is equals to your GCNR. Okay, ground coverage ratio. If you have the module, okay, so a higher GCR indicates a denser arrangement of modules. Of course, because W will be something, for example, if W is 13 and your pitch is 20, then 13 by 20 is what? 13 by 20 is 0.65. So your ground coverage ratio is 65%, which means your modules are closer. If the rows have much difference, if the rows have a high pitch, I would say 25 feet, then they are much apart. So a higher GCR means the rows are denser. A lower GCR means the rows have a good distance in between them. Their pitch is high. Okay. So, um, well, again, understanding GCR is important not just for energy yield, but also for the structural integrity of the system. A higher GCR might lead to increased shading between modules, potentially decreasing overall efficiency because, again, the pitch is involved in it. Conversely, if spacing is too wide, it may limit energy output. Okay, if the spacing is too wide, it may limit energy output. Installers should also consider environmental factors like winds and snow loads, which may necessitate adjustments to module height and spacing for stability and safety. And Well, I think uh, for height, I would say that yeah, and like I said, the heights are different for different installations. Ground mounts have around 3 to 6 feet. For of course, for a too high system, it will be more than 3 feet. I was just talking about a single high system or single high row, a single high module row. But for a too high system or for a too high row, it will be more than that, of course. So yeah, I think mastering these installation rules and calculation is essential for effective rooftop PV system, ground mount fixed tilt system, and carport system. Thank you for your attention, and I look forward to our next discussion. If you found this video helpful, don't forget to like and subscribe. Thank you very much. See you in the another one.